Picture this. You've just spent millions of dollars, years of your life building a revolutionary new robot. The prototype is finally assembled, the software is loaded, you push the button, it whirs to life, and immediately smashes into a wall. Why? All because of one single, tiny line of faulty code.
Yeah, just one tiny, unforeseen error in this incredibly complex dance between software and hardware. A miscalculation so small you'd never, ever catch it on a blueprint.
And just like that, you've got a catastrophic, expensive failure that sends the entire project right back to the drawing board. This is the absolute nightmare scenario for every robotics engineer on the planet. So that really is the million-dollar question, isn't it? How do you test a robot that doesn't even exist yet? How do you find those tiny, disastrous bugs before they cost you a fortune? Well, it turns out the answer is fascinating. The answer is simulation. You build its digital twin, a perfect physics-accurate copy of your robot living inside a virtual world. It's a place where you can crash it, break it, and rebuild it 1,000 times a day. And the only cost is a single click of a mouse. And you know, when it comes to building these digital worlds, one of the most powerful tools out there is the Gazebo Simulator. So today, we're going to pop the hood and see exactly how this whole thing works. Now, Gazebo's been around for a while, since 2002 actually, but the version we're digging into today is the modern Gazebo Sim. It's a complete redesign from the ground up, built to be way more modular and flexible. And with the old classic version getting retired in 2025, everything we're about to see isn't just history, it's the future of robot development. Okay, so this is our map for the journey. It might look a little complex, but at its heart, it's actually pretty elegant. Everything is organized through something called an entity component system. Just think of an entity as any object, a robot, a wall, a camera, and components are just the properties that define it, like its shape or its color. This system is what lets the two sides, the server and the client, work together perfectly. We're going to keep coming back to this map as we uncover each piece of the puzzle. So let's start on the left side, the server. The best way to think about this is as the engine room of our digital reality. It's the invisible powerhouse that's doing all the heavy lifting behind the scenes. This is where all the real work happens. The server is constantly calculating physics. Gravity, collisions, friction, the whole deal. It's generating these streams of realistic data from virtual cameras and lasers. It processes every single command, from the moment you hit play to the precise signal that tells a robot's wheels exactly how to turn. This is the absolute source of truth for the entire digital world. All right, so we've got our engine. Now let's hop over to the other side of our blueprint. If the server is the engine, then the client is our window into that world. It's the part we can actually see and touch. Here's the perfect way to think about the difference. The server is the powerful engine, right? It can even run headless. That means with no graphics at all, just crunching numbers in the dark. The client, on the other hand, is the interactive cockpit. It's the graphical user interface that lets us see the world the engine is building and gives us the controls to fly it. And man, this client can visualize anything. It could be a super simple robot on a clean, empty grid, or it could be a sprawling, absolutely chaotic warehouse filled with autonomous forklifts and digital workers. The client's one and only job is to translate the server's raw data into a living, breathing 3D world that we can actually make sense of. Okay, so we've got our virtual world and we have our virtual robot. But how does the robot's actual control software, its brain, talk to its new digital body? This is where the magic really happens. The connection is made through a special tool called the ROS-GZ bridge. Honestly, the simplest way to think about it is as a universal translator. See, the robot operating system, ROS2, it speaks one language, and Gazebo speaks a totally different one. The bridge just sits in the middle and translates between them perfectly and seamlessly. So the robot's brain can send commands like turn left and get all the data back from its virtual sensors. So let's take a step back and see what we've actually built here. We have a powerful, limitless sandbox where we can design, test, and perfect robots at lightning speed, all with zero risk. Let's look at our map one last time, now with all the lights on. The server, our engine, is calculating all the physics, building the world from those entities and components. It streams that reality over to the client, our visual cockpit, and using that bridge, the robot's actual software brain plugs right in, controlling its virtual body and seeing through its virtual eyes. It is a perfect digital feedback loop. And this is why it's such a game changer. The source material really hits the nail on the head when it says, this whole process is crucial because it lets you verify your design without spending a single dollar on hardware. You can find all the flaws, you can optimize performance, and you can train the AI all before a single screw is ever turned in the real world. Now, Gazebo is a huge deal, for sure, but it's not the only game in town. It's part of this really rich ecosystem of powerful simulators, each with its own strengths. You've got things like Webots with its awesome development environment, and NVIDIA's Isaac Sam, which gives you these mind-blowing photorealistic graphics for training AI.
So we've seen the blueprint. We know how all the pieces connect to create this incredible digital sandbox. But what happens when you try to simulate not just one robot, but 100? Or an entire city? What happens when this perfect system is pushed to its absolute breaking point? That is our next story.
Hurry, hurry!